Okay, so so today we will start a new title. We are discussing continuous functions, and first we will state a theorem which tells us how to construct continuous functions, new continuous functions from old ones. So let x, y, and z be topological spaces. Uh, then we have the following. First, constant functions. If f from x to y maps all the points into the single point y0 of y, then f is continuous. So constant functions are continuous, and then we have inclusions. Okay, if A is a subspace of X, the inclusion map let's call it J from A to X, sending any A to itself. Okay, is continuous. Of course, here X has its topology, and A has the subspace topology. Okay. Third one is composites. If f from x to y and g from y to z are continuous functions, then so is the composition G composition f from x to z. This function is also continuous. Fourth one is restricting the domain. So what is this? If f from x to y is continuous and A is a subspace of X, then the restriction function, restriction function, restricted actually function. What is this? So we denote it this way, from A into Y. How it is defined? Well, it is defined the same way as f is for all x in A. We only restrict the domain of f to the subspace A. Then this thing, then this function, new function from A to Y is continuous. Okay, and we have E, restricting or expanding the range. Expanding the range. So what is this? uh, if from x to y is continuous, and if A is a subspace of X, sorry, uh, let okay, şöyle yanlış yazıyormuşum. Be continuous. If Z is a space, is a subspace of Y containing f of x, then the function f, or maybe I should say g from x to z, given by g of x equals f of x. Then this is continuous, obtained by restricting the range of f to z, okay, is continuous. Similarly, if Z is a space containing Y as a subspace, then H from X to Z given by, again, the same rule. H of X is equal to F of X for all X in X is also continuous. And finally, okay, local formulation of continuity. This is really important. Okay. A map f from x to y is continuous if x can be written as the union of open sets let's say u alpha, such that the restriction of f to each u alpha from u alpha to y is continuous. Okay. Now let's see why this results are true. First, we have the constant map from x to y, so that f of x is equal to y0 for all x in x. Well, this is continuous. Why is that? What is the inverse image of any set? If U is open in Y, then what is the inverse image of Y? Inverse image of U. This is either is equal to X if y0 is in U, and this is the empty set if y0 is not in U, right? This is the constant function. Everything is mapped to a single point, right? So let me draw you a picture. And here is y0. Everything is mapped here. All these points are mapped to this single point, okay? y0. So if you choose your open set U like this, okay, then inverse image of this is empty because no point of x is mapped into U. However, if you choose your U like this, then of course inverse image of this is the whole space X because everything is mapped into U. Okay. In either case, these inverse images X or empty set are of course open. Therefore, F is continuous. Okay. Since both X and the empty set are open in X, F is continuous. Okay. B was the inclusion, I guess. Yes. So I have hangi statement'ı? B'nin mi? Yazacağım gerçi de. Okay, here is the statement. Inclusion. If A is a subspace of X, then this inclusion is continuous. So A is a subspace of X, and we define a map from A into X, so that J of X is equal to X. Okay, for all X in A. Sorry, X in A. Okay. Now I want to show that this map is continuous. So let's take an open set in X. Let U be an open subset. Open subset. Then what is the inverse image of this gadget? J inverse of U. What is this? Well, this map A, J does nothing, right? It just takes the point X and sends it into itself. What is the inverse image of this? That inverse image is the set of all points in U that are contained in A. So this is nothing but U intersection A. But what is this? This is just the definition of an open set in the subspace, right? Which is clearly open by the definition of subspace. Hence, J is continuous. All right. What about part C? Compositions. That's also easy. So if so, let F from X to Y and G from Y to Z be continuous. Okay. Then for any open set, let's say U in Z, the pre-image image. So I look at what under G composition F. So this is from X into Z is what? G composition F inverse image of U. Well, that is the set of all x's in X such that G composition F is equal to is in U, right? But this is the same thing as what? This is the same thing as uh, X is in X and uh, F of X is in G inverse of U, right? And this is what? This is just, and this is an open set, right? This is an open set. So this is just F inverse of G inverse of U, right? So where G inverse of U is open, since G is continuous, hence F inverse of G inverse of U is open, since F is also continuous. Therefore, thus G composition F from X to Z is continuous. Okay. All right. What about part D? Restricting the domain. So I have F from X to Y, and that is continuous. That is given. Okay, continuous. And A is a subspace. And G is this function, not G. Okay, let me call it G. This is the restriction of F to A, from A to Y, where G of X is nothing but F of X for all X in X. So what is G inverse of U? Then for any open set U of Y, we have what? What is G inverse of U? Well, this is nothing but all elements in A such that G of X, which is equal to F of X, is in U. Well, so what is this then? Well, this is just the inverse image of F of U under F, but you don't take all the points, you take the ones contained in A. So this is nothing but F inverse of U, right, from this, but those points should be from A. So it is this one, okay? However, F inverse of U is open in X since F is continuous. F is continuous. And thus, G inverse of U, which is just the intersection of an open set of X with A, is open in A. Okay? All right, so this proves part D. What about E? Now we have F from X to Y, again continuous. Uh, okay, and uh, it has two parts. The first part is this: Z is a subspace of Y, but it contains f of x. Okay, so we have something like this: subspace, subspaces. F of x is a subspace. Z is also a subspace containing this. And I consider the following function: g from x into z, such that g of x is defined to be f of x for all x in x. And I want to show that g is continuous. Well, let U be an open subset. Open subset. Then, what is the inverse image? G inverse of U. Well, this is the set of all x's such that g of x, which is equal to f of x, is in U. So what I am doing is then I look at all the uh, uh, open sets. Oh, okay. I have to be a little bit careful here. I would say this is open. So inverse image of U under F is open, but we have to be careful. An open set in Z may not be open in X, right? So we have to be a little bit careful. No, an open subset in Z may not be open in Y, but we know this. Then what is this U? U is equal to Z intersection V for some open subset V of Y. Okay. Then what is G inverse of U? Well, this is just X in X such that G of X is in U. But G of X is equal to F of X. So this should be in U. Okay. However, uh, f of x is in, of course, f of x intersection u. No, f of x is in z intersection. No. So f of x is in u and yeah. Okay, what is u? U is just okay, let me write it this way. So this is just f of x is in u. But what is u? U is just v intersection z. Bakayım ben ne yazdım? Okay, v intersection z, yes. But what is this? I mean, okay. However, I know this. Yeah, this is the same thing as v. Why is that? Because f of x is already in z, right? Because since f of x is a subset of z, So there is no need to write f of x is in this intersection. It is already here. So this is equal to this one. Yes. And what is this? This is nothing but f inverse of v. And this is open, which is open in x, since f is x to y is continuous. Right, so the critical thing is here, f of x is in this intersection. This statement is equal to this statement. So these two sets are the same, okay? Any point in x which is mapped into v uh, is mapped into v intersection z, because f of x by definition is inside x, is contained in z. And of course, if it is here, then it is here. Okay. All right. So this is the first part of it. And then there is this second part. Okay, second part. Let me also consider that one. This time we have this. F from x to y is continuous. And I have a space containing y as a subspace. Is a subspace. And h is this function from x to z, defined by again with f of x for all x in x. And I want to show that h is continuous. So let u be an open subset. Then what is the inverse image of u under h? So h, okay, then h inverse of u, what is this? This is the set of all points in x such that h of x lies inside u. But h of x by definition is equal to f of x. So this has to be inside u. However, we know that uh, image of f is contained already in y, because f is a function from x to y. Therefore, this is the same thing as this. F of x is in u intersection y. Okay? Because image of f is contained here. So again, these two sets are the same. Okay? These two sets are the same. But what is this? What is this? This is just f inverse of u intersection y, which is open. Which is open. Why is that? Since f from x to y is continuous and y intersection u is an open subset. Subset of y, right? Because u is an open subset of z, y is a subspace of z, therefore u intersection y is an open subset of y. Since this is an open subset and f is a function from x to y, its inverse image is open in x. All right, the last one. Okay, local formulation of continuity. So this is something very important. So x, let's say, is a union of some open sets. This can be finite or infinite union. And I have a function from x to y, so that restriction of f to each u alpha from u alpha into y is continuous for each alpha, for all alpha. Okay, then we want to show that f is itself continuous. So if f is continuous on every open set, then and if this open set covers the whole space, then f is continuous. Okay, how can we check this? Well, okay, so let v be an open subset of y. Then what is the inverse image of v? Okay, well, this is a subset of x, right? Subset of x, and therefore this subset is what? This is f inverse of v, okay, intersection x, right? Because this gadget is contained already in x. But I write it this way because of the following. This is f inverse of v intersection. So I have this union, okay. What is this then? Well, this is equal to the following. This is the union of intersection of v, intersection of f inverse v with u alpha. Okay, but what is this? This is nothing but, you see, if so, f is a function from x to y, and let me say f alpha be the restriction of f to u alpha. So this is a function from u alpha into y, given by the same rule, okay? Just the restriction of f to u alpha. Then this thing is nothing but f alpha inverse of v, okay? Why is that? So this means what? I am looking at all the points in u alpha that are mapped into v. Well, this is exactly this gadget, right? And I know that each f alpha is continuous. Restriction of f to each u alpha is continuous. Therefore, each f of alpha, if each f of no f alpha is continuous, uh, therefore this is open. This is open since each f alpha from u alpha into y is continuous. Uh, okay, so since these are continuous, this is an open subset of bir dakika. Yok, biraz daha dikkatli olmam lazım. Şöyle diyeyim, pardon. Şurada biraz daha dikkatli olmam lazım. Okay. Şimdi şuna bakalım. Since f alpha is continuous, nereden tarifli bu da? U alfadan y'ye gidiyor. Is continuous. F alpha inverse image of v is open in u alpha. Okay. However, u alpha is open in x, and thus f alpha inverse of V is open in X, right? This set is open in U alpha and U alpha is open in X. Therefore, this thing is open in X. So finally, F inverse of V, right? F inverse of V, this thing, which is the union of these gadgets. And now I know that each of these are open in, I don't need this parenthesis. Each of these are open in X. So this is a union of open subsets of X. Therefore, it is open in X. So this is union of F alpha inverse of V, right? Yes. Which is a union of open subsets of X is also open. So inverse image of V under F is open, thus F is continuous. Okay. Sorusu olan var mı buraya kadar? Okay. This thing is not true if we replace open subsets with closed subsets, and actually it's I guess one of your exercise problems. However, the finite version of this is true. Okay, so let me write it this way. So part neydi onun ismi? Local formulation of continuity doesn't work if we replace open subsets U alpha with closed subsets. Okay, so if I restate this local formulation, but instead of open subsets, if I take closed subsets, so X is a union of closed sets, and F restriction of F to each of these is continuous. Okay, then whether F is continuous or not, well, that's not true. So F may not be continuous. Okay, however, if we have finitely many of these subsets, then it works. However, for infinite unions, şöyle yazayım. However, it works for finite unions as the lemma below shows. Okay, now let me state the lemma. Sorry. Lemma. Its name is the pasting lemma. You have probably seen this before, but let's write down. Okay, so let X be union of A and B, where A and B are closed subsets, closed subsets of X, and we have, let's say, two functions defined on A and B. Let f from A to Y and g from B to Y be two continuous functions. Uh, of course, here A and B has this subspace topology where A and B are uh, endowed with the subspace topology. Space topology. Okay. Assume that these two functions agree f of x equals g of x for all x in the intersection, okay, of this closed subsets. Then the function h from x to y defined by şöyle tarif ediliyor. H of x this is equal to f of x if x is in A, and it is defined to be g of x if x is in B. Well, this is well defined because if x both belongs to A and B, then it doesn't matter which one you choose, f or g, because they are the same. Then this function is called is continuous. This is called pasting lemma because you have two patches. You may think it this way. Your space has two subspaces A and B, and f is defined here, g is defined here, and they agree on this intersection, and altogether they give us a function h. It is defined as f on A, it is defined as g on B. And this is nothing but, we paste two functions f and g and obtain a function on the whole space x. Okay, that's why this is called pasting lemma. And proof is very simple. So let U be an open subset. Okay. Then what is H inverse of U? Okay. Well, this is what? So this is the set of all x's in X such that H of X is in U, but H is equal to F or G depending on what? Depending on whether X belongs to A or not. So this is, I can write it this way. This is f of x is in U if f of x is inside, no, if x is in A. But actually I can write it this way. So yes, and okay, x is in B And if X is in B, then my H is equal to G. So G of X is in V. No, U. So what is this then? This is nothing but F inverse of burada open set almayayım. Sorry. Let's take a closed set. Let okay, K be a closed subset. Okay. You will see why I choose closed. It doesn't matter, right? I mean, I can use either open subsets or closed subsets to check continuity. Okay, so this is equal to what? This is just the inverse image of K under F union, and this is just inverse image of uh, K under G. Well, uh, since F from A to Y is and G from B to Y are continuous, F inverse of K is closed in A, and G inverse of K is closed in B. However, A and B are closed sets in X. Okay, since A and B are closed in X, F inverse of K and G inverse of K are both closed in X. So this is closed in X, this is closed in X, and I have only two of them, therefore their union is closed. Hence, H inverse of K, which is F inverse of K union G inverse of K, is closed in X. Okay, and this finishes the proof. So that H from X to Y is continuous. All right. Now, I will tell you why this doesn't work. Well, actually, it is clear why it doesn't work for uh, arbitrary unions, infinite unions, because in that case we wouldn't have just two sets, but we would have infinitely many closed sets, and union of infinitely many closed sets may not be closed, right? So when you take finitely many of them, their union is closed, but if infinitely many of them wouldn't be closed. Therefore, this proof wouldn't work for infinite unions. Okay. All right. Let me stop here. I'll continue in the second hour.